So by this time in your math career, you should be pretty comfortable with the concept of slope. Slope is the rate of change of the y values on a line. So if I change my x value by 1 and my y value jumps up by 2, that's a slope of 2 divided by 1 is 2. And for a straight line, that slope is the same everywhere on the line. In fact, that's what makes it a straight line. On this graph right here, you're going to see some points plotted. This point right here has an x value of 0 and its y value is 1. I'm using this function 2x plus 1. So 2 times 0 plus 1 gives me the y value of 1. 2 times 2 plus 1 gives me a y value of 5 for this point right here. And if I draw the line 2x plus 1, it passes through those 2 points as it should. Let's look at the slope calculation down here. We have f of b. Okay, our f is 2x plus 1. If we plug in b equals 2, we get 5. So f of b is 5. F of a, where a is 0, is going to be 1. We're going to subtract them. So this is y2 minus y1, nothing more than that. Here we have x2 minus x1, which is 2 minus 0. So 4 on top, 2 on the bottom gives me a slope of 2, which is pretty obvious from the equation of this line here. You should become comfortable with the function notation as you see right here, because this is going to allow us to generalize a lot of the operations and formulas and results that we get so that we don't always have to refer back to any particular function. Reason for saying that, I can demonstrate here. Let me shut off this graph here, and I'm going to select a different function, x squared plus 1, and I'm going to keep these points the same. So when a is 0, then f of a is still 1. 0 squared plus 1 is 1. And when b is 2, f of b is still 5. 2 squared is 4 plus 1 is 5. And so this gives me the exact same calculation as I have down below here. As a matter of fact, any function graph that passes through these 2 points, regardless of what it looks like in between those points or beyond those points, is going to give me the same rate of change between those 2 points. So we call this the average rate of change. So even though a straight line between those 2 points has a different slope, we can see that this slope is changing, and so if we were to average all those slopes together, we would get this slope from this calculation. If I go back to my straight line for a moment, I want you to watch this calculation over here as I change a and b. Because this is a straight line, the slope, the rate of change, never changes regardless of my positions of a and b. They can be in front of or behind each other like this. They could be at any particular points along the x-axis here, and I'm always going to get a value of 2 because that is the slope of that line. So if I set these back here and go now to x squared plus 1, watch the calculations over here as I move b. We get a different value because now I don't have that constant slope. I don't have a linear function. And so the average rate of change then is going to be a tool to allow us to calculate the slope as we get closer and closer to 2 points, giving us the tangent line. Now what I want you to notice here is if you look at this calculation as I move b closer and closer to a, my secant line should become my tangent line, but when they become the same point, both the y value at this value of x and this y value at this value of x are both 1, and both values of x are 0. So I get 1 minus 1 over 0 minus 0, and my slope is undefined. So we can calculate average rate of change as an approximation for instantaneous rate of change, or slope at a point. The problem is we cannot do a simple calculation like this because when we get those 2 points together, we're going to get 0 over 0.